Hi friends, today we will talk about matrix and operation on matrix, the rank of matrix, and etc. So let's start. What is matrix? In mathematics, a matrix is a rectangular array or table of numbers or symbols or expressions. As you see, the numbers are arranged in rows, which are horizontal, and columns, which are vertical. For example, the dimension of the matrix below this matrix is 2 by 3. 2 by 3. This first number represents the number of rows. As you see, there is 1 and 2 rows and 3 columns. 1, 2, and 3 columns. If the matrix has 2 rows and 1 column, it is column matrix. This matrix is 2 by 1 and it's called column matrix. And this one is called row matrix because it has 2 columns and 1 row. It is 1 by 2 and this is row matrix. This remaining matrix is 2 by 2 and this is square matrix because it has the same number of columns and the same number of rows. Provided that 2 matrix has the same size, for example, it has the same number of columns, each matrix has 2 columns, and this also 2 columns, and has the same number of rows, 2 rows here and 2 rows here. We can add or subtract the elements one by one. For example, if we want to add 2 matrices, we should add each number respectively. For example, 5 plus 6 is 11, 3 plus negative 7 is negative 4, 2 plus 0 is equal to 2, and 8 plus 4 is equal to 12. Also, we can subtract this matrix. If we want to subtract these 2 matrices, we will get, let me write it here, 5 minus 6, negative 1, 3 minus negative 7 is equal to 10, 2 minus 0 is again equal to 2, and 8 minus 4 is equal to 4. And this is addition, and this is subtraction of 2 matrices. The addition and subtraction of 2 matrices is commutative. As you see, we can reorder the matrices and the result will be the same. And what about the multiplication of 2 matrices? The multiplication of matrix is not commutative. If we reorder the matrix, we will get different result. In order to find the multiplication of 2 matrices, we should multiply the first row of first matrix by the first column of second matrix. Again, it will continue. Now I will explain how should we do it. Okay, first we should multiply 5 by 6. 5 times 6 plus 2 times 0. 2 by 0. And this is our first element of the resulting matrix. Again, 5 times, we should multiply this row by this column. 5 times 7 plus 2 times 8. Again, let's continue. We will do the same operation by the second row. 2 times 6, let it be 3. Okay, because 2 is here, and let it be 3. 3 times 6 plus 7 times 0, 7 times 0, and 3 times 7 plus 7 times 8. 3 times 7 plus 7 times 8. And here, what will we get? 30, if we find the result. 51 here. 18 here. And 77, this one. This is the multiplication of two matrices, and don't forget, the multiplication of two matrices is not commutative. A submatrix. What is a submatrix? Submatrix of a matrix, let it be the given matrix A, which consists of 3 rows and 1, 2, 3, 4 columns. This matrix is 3 by 4. A submatrix of a matrix is obtained by deleting any collection of rows and columns. For example, from this given matrix, we can construct a 2 by 3 submatrix by removing row 2, for example, and column 3. If we remove this row and this column, what will we get? We will get the remaining elements are 1, 2, and 9. Nine, 10, 12. Now we get a submatrix of this matrix. Sorry, this is not equality. The given matrix is 2 by 3, as you see. The determinant. The determinant of a square matrix A is a number encoding certain properties of the matrix. For example, a matrix is invertible if and only if its determinant is non-zero. Its absolute value equals the area or volume of the image of the unit square. For example, this is our given matrix. If we want the determinant of this matrix, this is equal to the multiplication of diagonal elements A times D minus B times C. The determinant of 3 by 3 matrix involves 6 terms, and we will explain. For example, let's explain the determinant of any matrix. For example, A is equal to 3, 4, 5, 6. If we want to find the determinant of this matrix, we should multiply 3 3 by 6 minus 5 times 4, and 18 equal minus 20 is equal to negative 2. So the determinant of this matrix is negative 2. Let's find the determinant of 3 by 3 matrix. What should we do? Again, let's remove first column and first row. The leading element of this row and column is 5, and we should write 5 times, what is the submatrix? We removed this row and column. The submatrix is 3, 5, negative 2, and 3. Negative 2 and 3. Let's continue. I'll remove these lines again. Okay, let's continue. Now it's time to remove first row and second column. The leading element of this intersection is 0. The first sign of this multiplication is positive. Now we should write negative. 0 leading element, 0 times, what is the submatrix? Submatrix is 2, 5, yes, and 1, 3. 2, 5, 1, 3. Because we removed this to row and column. Again, we will continue. Let's remove first row and third column, and the leading element of this intersection is 3, and first sign is positive, second is negative, and third one should be positive. Positive 3 times, what is the submatrix? 2, 3, 1, negative 2. 2, 3, 1, and negative 2. We have studied how to find the determinant of 2 by 2 matrix, and it's equal to 3 times 3 minus 5 times negative 2. Okay, I didn't find the solution of this operation, because if we multiply 0 by any matrix, we will get 0 again, and this is wasting of time. And let's continue. 3 times 2 by negative 2, or not plus, sorry, minus 3 times 1, and it's equal to 5 times 19 plus 3 times negative 7, and this is equal to 74. This is the determinant of 3 by 3 matrix. But what about 4 by 4 matrix? If we want to find the determinant of 4 by 4 matrix, we either can use the above operation, this operation, or another way is finding the multiplication of the diagonal elements. The multiplication of these diagonal elements. But here we have a case. The remaining element under the diagonal elements should be equal to 0. These elements should be equal to 0. In order to get such type of matrix, we can do some operations on columns and rows. For example, we can interchange the rows and columns, or we can add rows and columns. Row and column operations don't change the determinant. If we interchange them, the determinant will be the same. But interchanging row and columns change the sign of determinant. Let's find out. Let's see the example. This is given matrix. Here you see the diagonal elements are 1, 9, 1, 3, but the elements under the diagonal elements are not 0. Here 2 of them are 0, but 4 of them are not 0. We should get 0 from these elements. What should we do? We can find the twice of row 3 and subtract it from row 4 and write the result instead of row 4. Let's find. As you see, we do operations on row 4 and row 3. This means that row 1 and row 2 remains the same. What have we done? We find the subtraction of row 4 here and 2 times row 3. We will get 0, 0, 0, 1, and we wrote this row instead of row 4. Our new row 4 now is 0, 0, 0, 1. And this is the diagonal elements. Again, 2 of these diagonal elements are not 0. So we should continue the operation. Again, what should we do now? Let's interchange row 3 and row 2. Row 3 is this and row 2 is this. Let's interchange them. So this is the new matrix. Again, let's see the elements under the diagonal elements. 2 of them again are not 0. So let's continue the operation. What should we do now? Let's multiply row 1 by 3 and subtract it from row 3 and write the result instead of row 3. So row 3 should be equal to row 3 minus 3 times row 1. Let's do this operation. New matrix is this, and if we find the diagonal elements, the remaining elements under these diagonal elements are 0. Yes, now we can find the determinant of this element. The determinant of this element is equal to the multiplication of the diagonal elements, 1 times 2 times 2 times 1. But as we mentioned above, the interchanging rows and columns change the sign of determinant. So in front of this brace, we should write this negative sign. And our result is negative 4.